Hello, class. Today we're going to be talking about the theory of continental drift. I like to start off this with a quote. It's from a renowned geologist, Chester R. Longwell, who said, "If the fit between South America and Africa is not genetic, then surely it is advice of Satan for our frustration." And we'll see what he meant in just a little bit. So to give a little bit of an overview, how has our Earth changed? Now that we've discussed the structure of our Earth and the mechanism by which plates move, we can analyze how the appearance of Earth has changed over time. Notice on the graphic that the continents have not been static in their positioning, and that over time they have appeared to separate or drift apart. Here in the Permian, we can see that we have Pangaea existing over 225 million years ago, and then in the Triassic they begin to separate and move apart. Further separation in the Jurassic, and again even further separation in the Cretaceous, and then here we are in our present day with the continents spread much further out. So we're going to focus mainly on Alfred Wegener's theory of continental drift. Now, the concept of large-scale movement of the continents has been around since about the 16th century, but it wasn't until 1915 when the German meteorologist Alfred Wegener proposed his hypothesis that the continents drift over time that it really entered the scientific consciousness as a possibility. In addition to his theory of continental drift, he also hypothesized that at one time all the continents were joined together as one large supercontinent, which he called Pangaea. So, continental drift is supported by these four major pieces of evidence. We have continental fit, we have fossil evidence, such as the Mesosaurus, we have related rocks, and we have ancient climates. Now we're going to talk about a little bit about each of these pieces of evidence. So, continental fit is like the world's largest jigsaw puzzle, and it's the foremost feature of continental drift in that the shape of the continents kind of fit together. So if we rearrange the continents, like has been done in this picture, we can see that they fit together rather well. And there stands to reason that the only reason that they're shaped this way is because at one point they were part of a larger whole, which was what prompted Wegener to first create his theory. Next, we're going to be talking about fossil evidence. So fossils collected across the globe show us a very interesting pattern. As the graphic on the right depicts, fossil evidence of these now extinct organisms span across the separate continents. Here we have the Mesosaurus, which was located in South America, but also in South Africa. Now, the only way the Mesosaurus could evolve into the same exact creature and exist in these now separate environments, the only way its fossils could have been there is if the southern part of South America and the southern part of Africa were at one point joined. So, again, we can assume that in order for this pattern to occur, that the continents would have had to have been connected during an earlier time of the Earth's history. Another very popular fossil that you'll hear that will be referenced a lot when we discuss the theory of continental drift is the Glossopteris, which is this plant down here. And it's very important because it spans across, all these different continents. So it was a very key piece in further establishing the theory of continental drift. Next, we're going to talk about related rocks. So just as we can observe patterns in the locations of various fossils when we fit the continents together, we can also observe patterns in the rock record. Now, the matching assemblages of distinctive composition and origin are found across the continent, providing evidence that these formations were once a part of a large whole. So this large formation of rock between South America and Africa were at one point connected. So if they were forming during the same event, it means that they would have had to have been connected. And the only reason that that formation is no longer whole is because the continents have drifted apart. Lastly, we're going to talk about ancient climates. In addition to the large-scale movement of continents, the climate of the Earth has also changed dramatically over time. Evidence of past glaciations such as striations, till deposits, and formations like U-shaped valleys provide evidence of widespread glaciation while Pangea was still in existence. And we can observe our current environment for evidence of the presence of glaciers and their movement. An example would be glacial striations, which are shown here. So, when Pangea was still in existence, roughly 220 million years ago, there was a large glacier across Antarctica and the South Pole, part of South America, India, and Australia. And by examining features like striations, till deposits, and U-shaped valleys, we can assume that the glaciation must have been present on all of these different continents in order for these pieces of glacial evidence to occur at the same time and in the same orientation. So a big piece here is these glacial striations, which are these really thin scratch marks, which were actually created when hundreds and hundreds of meters of ice and snow as a glacier pressed down in this rock and scraped across the surface and created this big scratch. And as we can see from the line here, we can actually plot out how the glacier moved across. So as we can see here, when we have striations in South America and Africa, they kind of match. So the glacier would have expanded outwards here and outwards here and downwards here, downwards here and downwards there. And by examining these striations, we can prove that the glaciation existed when all of these continents were touching each other by correlating the orientation. Alright, well that wraps up the theory of continental drift. I'd like you guys to now answer the questions that I posted below, and I will see you all in class.